Now I want to say a few words about how to obtain parametric equations for a certain curve. The curve might come, for instance, from the study of motion. It can be the trajectory of a certain point in motion that you're studying. As I pointed out, very often you think of these parametric curves as positions x and y at a particular time t. Of course, the parameter you're choosing ends up being something different from time very often, but of course it can be time as well. Regardless, these parametric curves often come from the study of motion. So let's look at the case where I roll a circle along a straight line, and I'm looking at the trajectory described by this red point. Right? So I have a fixed point on the circumference, and I'm going to roll my circle and trace out the trajectory of the red point. You can think of that as a bicycle wheel, for instance, and the red point is the valve, and you're looking at the trajectory described by the valve as you go along with your bicycle. So let's look at what it looks like. So here what we have traced is a so-called cycloid, which is the trajectory of our valve. So how do we get parametric equations for that? Well, let's put ourselves in the xy plane and think of the x-axis as the straight line on which our circle is rolling. So here I have my circle rolling on the x-axis and in a particular position of the trajectory. And the first observation I want to make is that if you roll back the circle in its initial position and you try to see what is the part of the circle that makes contact with the x-axis, try to think of that as you watch this. Okay, so look at the part of the circle that makes contact, and you see that this part of the circle that has made contact is going to have, of course, exactly the same length as this red line segment and the x-axis, and this is this red arc on the circle. So these two things have the same length, and it's essentially we've rolled this red segment onto the circle. So let's introduce some notations where C is the center of the circle, T the point of tangency, the point of contact with the x-axis, P the position of the point of interest, right? Namely the point that is going to describe the trace out the red curve, the cycloid, or the radius of the circle, and theta, the angle at the center here, the angle TCP. Then the distance OT, the red line segment on the x-axis, is the same as the length of the arc on the circle from T to P, and this arc has length r theta, simply because it is, if you think of the circumference where the angle is 2 pi, then you get 2 pi r. And then the part of the circle that you're tracing is really proportional to the angle. So if the angle has radian measure theta, then instead of 2 pi r, you get theta times r. Now, in the case where theta is 2 pi, you get 2 pi r. So that's the length of this arc on the circle TP, and therefore of the line segment OT. So that gives us a way to calculate the x-coordinate of P, because now this x-coordinate is going to be OT minus QC, and QC is something that we can calculate because this angle here, as you can easily see, is pi minus theta, and in this right triangle PQC, that is with right angle at Q, the segment QC is the opposite side to pi minus theta. The hypotenuse has length r, and therefore QC is r sine of pi minus theta, but of course sine of pi minus theta is the same as sine theta. So we get that QC is r sine theta, and therefore x, which is the difference, is r theta minus r sine theta, and we can factor out r. So now we need to find the second coordinate y as a function of our parameter theta. So you can see that y here is the length from the point where I have written x on the x-axis to q, so that's the same as the length tc plus the length qp. So this length tc is just a radius, so it's r, and so what we need to find is this qp distance, which we can again calculate in the same right triangle. Now this is the adjacent side in our triangle, and therefore its length is r multiplied by the cosine of pi minus theta. The cosine of pi minus theta is negative cosine of theta. Therefore what we obtain is r for tc and negative r cosine theta for qp, and factoring out r, we get r 1 minus cosine theta. And this way we found a pair of parametric equations for the cycloid, and the parameter theta can take essentially any value if we keep moving in one direction or in the other, and taking theta from 0 to 2 pi corresponds to the first arch in the cycloid, and of course if we go all the way to 4 pi then we get the two arches as drawn on top, and of course what has been drawn so far is just from 0 to 4 pi. But in general we could change the value of theta to another interval. We would just get more arches. So now in the next video we're going to look at ways to study these parametric curves a little bit more carefully using calculus, how to find tangent lines, and how to find arc length, area enclosed, these type of things.